Spari po I them disa fjalë në gjuhën shqipe, pastaj e kthejmë në anglisht. Shpresoj që jeni mirë edhe mirë se vini në seminarin e radhës të departamentit tonë, ku përfolës kemi ish studentin e departamentit, Islam Foniqin. Kemi kënaqësi që të kemi Islam. Atëherë si zakonisht I kemi rreth 50 minuta për prezantim e pastaj pjesa tjetër për pyetje komente. Edhe kur do të keni në pyetje ju lutem direkt ngritini dorën ose merrni fjalën. Okay, now I will switch to English, and I have the pleasure of introducing our next speaker in our math department seminar, Islam Foniqi, Dr. Islam Foniqi from Norwich, who actually used to be our student, and we are very proud of him. He will be speaking about decision and algorithmic problems in algebraic structures. So now, Islam, the floor is yours. You can take it over from here.
Okay, thank you, Chandran, for the introduction. It's a pleasure for me also to speak at the department where I did my undergraduate studies, and hopefully in person as well. Also. Okay, so the talk is about decision on algorithmic problems in algebraic structures. And in the first part of the talk, I would try to explain stuff that is in the title. But first, I wanted to start with a warm-up game. So we have this game where we can choose a natural number and we can repeat the following procedures as many times as we desire. If our number n is even, we divide it by 2. If it's odd, we multiply by 3 and add 1. And one example would be if we start with 1, then 1 is odd, we go to 4. 4 is even, we go back to 2. And even, we go again back to 1. And this procedure repeats. So we just get the cycle 1, 4, 2 many times. So another example would be with 12. And we get this kind of a sequence. And we saw that once we arrived at 1, it's not interesting anymore. It just repeats. So one interesting question would be to know if we always reach 1, regardless of where we start with that. And as far as I know, as of yesterday, this question is still open. And it's actually a conjecture known as Collat's conjecture, or sometimes also 3n+1 conjecture. And the conjecture actually says that this process reaches 1 for every n. Okay, this is not entirely in the decision problem form, but I will try to make it that way. So for now, I define this set C, yes, which is just the set of natural numbers where we reach 1 when we start with that. Okay, and the decision problem is basically a problem with a yes or no answer on an infinite, usually countable set of inputs. So we have countably many problems where we can decide for each one of them, yes or no. We can answer each of the questions with one of these answers. Okay, and one of these examples would be if we choose 2 natural numbers and we can ask, are they relatively prime? Okay, this set, the set of inferences for this problem is any tuple in n times n. So it's countably many such tuples. And for any tuple, we can answer yes or no if they are relatively prime or not. And actually, this one is decidable because we have Euclid's algorithm. And it's something we can also write in a computer and decide for every pair. Another similar problem would be if we start with triples now in N3, and we can ask if they form a right angle triangle. And again, we can write something in a computer which decides that for us, and it works uniformly for every triple. And the third problem, it's something coming from topology, and it asks if you give two simplicial complexes, can you decide if they are homeomorphic? And okay, the range of here again, the range is the tuple of simplicial complexes, and this can be made to be countable. And for any instance, we can answer yes or no. But actually, this is something that we cannot decide with only one algorithm. And this is a problem that passes through something that is called the isomorphism problem in group theory, which I'll discuss it a bit later. Okay, and then we have this definition that when we have a subset of natural numbers, we call it decidable, or sometimes it's called also recursive, I think. And we call it decidable if there is an algorithm that takes any natural number as an input, and it terminates in a finite time. And the amount of time it takes might depend on the number n. But the point is that it tells us correctly whether n is in the set S or not. Okay, and one question that we can ask is the Cantor yes set decidable enough? And this is also open because in the conjecture says that this is equal to n, and in that case it would be, but so far we don't know. And here are just some key points of algorithms to have into account. The first one is that they have a finite nature, so they should have finitely many steps, and like something you could write in a computer. So no infinite lengths are allowed. Also, infinite loops are not allowed, as if you enter an infinite loop, you would basically take infinite amount of time, which is not something we want. And we call decision problems decidable, which is the same word I used also for subsetting out. If there is an algorithm which takes where the inputs of the algorithms are instances of the problem, and in a finite amount of time, it terminates with either yes or no answer. And one important thing is that the algorithm has to come first and then apply the instances to it, not take an instance, apply it on algorithms, as we would get infinitely many algorithms that do the job, but not uniformly. But yeah, this is the point that we don't want implementing many algorithms, one done for each instance, but we want an algorithm that takes instances and gives answers. Okay, and in the 30s, in the area of logic, Church and Turing proved that there are actually decision problems that you cannot decide, like you cannot find algorithms to decide them. And one implication is of their theory is that there are sets in natural numbers that are not decidable. And one philosophical proof of this would be that the set of algorithms we can form is in a sense countable, and there are uncountably many subsets of n. So there must be something that we cannot get by an algorithm. Okay, and then it took a bit of time for these problems to also go to the other areas of mathematics. But in the 50s, there was some theory where undecidability problems come also to monoid and group theory. Okay, and this was about decision problems, and now I'll talk a bit about the algebraic structures that I'm concerned about. And this consists of monoids and groups, which is something I guess we all know. And then there is something in the middle called inverse monoids, and I'll try to define this a bit. Okay, so start with a set S and an operation from S times S to S. And yeah, S together with this operation satisfies this property by definition that usually it's called closure. Like whenever you apply the operation to two elements of S, you get another elements of S. But if in addition the operation satisfies the associativity property, then we call the structure a semigroup. If in addition there is an element which behaves like an identity with multiplication, like whenever you apply an element from left to right, by that you get just the element itself, then it's called a monoid. So in particular, a monoid is just a semigroup with identity. And if in addition to those, you get also inverses, for every element you get another element A prime or A minus 1, such that when you multiply them, you get the identity, then this structure is called a group. Okay, and here is just a list of illustrating this definition. So if you take the natural numbers with addition, you get a semigroup, and this doesn't have an identity. So it's not a monoid, and it's not a group as well. And then if you add the element 0 to addition, you get the identity, because 0 added to something just gives that thing back. But this is not a group, as the inverses are not there. And then you get the integers with addition, which satisfies all the axioms and gives a group. Okay, then the other structure is a bit richer than monoids, but it's, I guess, in the middle of monoids and groups, which is called an inverse monoid. And this is just a monoid, but satisfies this property that every element has a unique, what it's called, I guess, semi-inverse. It's kind of a local inverse, and it satisfies these equations. And notice here, then we use the word unique in the definition, which is not something we get for free, like in the case of groups where the inverses have to be unique. Okay, and below I just illustrate what this means in a general sense. Like we take groups to be just an abstractions of symmetries. So to study symmetries of objects, we use groups. And monoids is, I guess, an abstraction of transformations, because it doesn't talk only about symmetries, but it talks also about other transformations, the ones that don't necessarily have inverses. And then there is inverse monoids, which it's a bit about partial symmetries. Like you can work with local symmetries and do not care about what happens on the rest of the object. And to illustrate this, think about a set and the functions from the set itself. And then if you talk only about the bijective functions, you get permutations of the set, and this actually forms a group, as every permutation has an inverse, and you also have the identity permutation. But you can also talk just about any function from S to S, and this set of function would form a monoid and not necessarily a group or inverse monoid. And then you could consider also this IS, which is just a bijection between subset of S. So these are functions that are defined partially on S. They are defined in a subset, but we don't know what happens outside of A. And actually this forms a inverse monoid structure, and the operation is just composition of functions, but composing wherever there is possible common domain to compose. Otherwise, the composition would be this empty function. And one way to think about inverse monoid would be just to think of a vector space, and you want to study proper subspaces. Like you can have isomorphism of proper subspaces, and you don't know how they are defined on the rest of the vector space, but you can either extend or do something else. Okay, and now I'll talk about the structures and the presentations. So given a finite set, which usually I call an alphabet, we denote by A star what is called the free monoid over A. And it's just all words that you can write using the letters of A. And there is one special word there, which is called the empty word, which is zero length, and it just reflects the identity in a monoid. And the operation here is the concatenation of words. For example, we have the empty word for the alphabet A, B, we have the empty word and these other words belonging to A star, and any other word that you can write with on the letters A and B. And for the presentation of this structure, I will use this notation, like GP stands for group, A is for the set of generators, and R for relations. And I guess we all know what this means. It's just the quotient of a free group on A, and you take the quotient from the normal closure of words in R. But for monoids and inverse monoids, the definition is a bit different, because we don't have a normal closure, but we have another notion of congruence. But right now, don't worry about that. I will talk a bit later about what this means. And for this, I don't need it right now, so I'll just use it as a notation. And here are some examples of groups and the structures with the presentation. So this is the group on only one generator and free of relations. And it's just taking all the powers of A, negative or positive, and this group would give just the integers. On the other hand, if we take the group on two generators and we impose commutation on those two generators, we get the whole grid Z squared. And similar thing for monoids. Here we can take only non-negative powers, because for monoid we don't have inverses, so the notation is that we can multiply only combinations of generators coming with non-negative powers. And this is just the additive monoid in N0. And similarly, if we impose commutation, we get N0 squared. And the inverse monoid structure is a bit more complicated. Like even in the free case where you have only one generator and zero relation, you get this structure that looks like Z, because the last element presents actually the point in the line. But it comes together with this interval minus LR where N belongs. And here is the multiplication operation, which tells us how this operation behaves. Even though here it looks complicated, it can become clearer with something geometric, which is called moon trees. But I don't need much about inverse monoids, so I'm not gonna go into details about this. Just to note that their structure is a bit more, in the first look, more complicated than groups and monoids. Okay, and the main decision problem that I will talk about today is the word problem. So let's start with the monoid in this presentation. And then the word problem for a monoid is called decidable if we have an algorithm that takes as input two words on the written with letters of A, and it outputs yes if those words are equal in the monoid, and no if they are not equal. And the first result is that the word problem is decidable in free monoids. And usually free monoids and free groups would be the main example where every decision problem I talk about today is decidable. So you could apply that for other decision problems as well. And a short proof of this would be just you start with an alphabet and you take the free monoid on that alphabet. You choose two words in the monoid, and then those words are equal if and only if they look the same letter by letter. So you start reading the first letter. If they differ, they are different. If the letter is the same, you still keep reading. And one could also write an algorithm in the computer about that. It's just a matter of they should have the same length, both words, and they should have the same letter in every position. And in the late 40s, there was one of the first results about undecidable things in monoids, and it actually says that there is a finitely presented monoid for which there is no algorithm to decide the word problem. And these results have been kind of become simpler, and the ones we know today can be made to have only three relations. So some generators and then three relations. And we know that if we have a monoid with zero relation, the word problem is solvable. But one could ask what happens for monoids with one or two relations. And this is actually still open, both of these questions. And in the area of groups, again, the word problem is decidable in free groups. And here again, there is a bit more to do than in free monoids, because you have to cancel the words x minus 1 or x minus 1x where they appear. But other than that, after you have done all those cancellations, every word is reduced and you just compare those pairs of words. And there is a similar result after. I forgot to say that the result about monoids usually use the fact that the natural numbers n have undecidable subsets, and then there is a way to encode that in using monoids, and you can construct a monoid to say that the word problem would be decidable if and only if the membership in that subset of n would be decidable, but that's already undecidable, so you get the result. And similarly for group as well, one uses the fact that one has monoids with undecidable word problem, and there's a way to encode that into groups. And I'll mention one result about that later. Okay, and the result about groups says that there are groups which don't necessarily have decidable word problem. But for groups, since their structure is richer than the monoids, it's difficult to get groups with low number of relations. So the best examples we know so far have 12 relations. It was when they published the results, it was actually 33, but there were some modifications to reduce the time. Okay, now I'll proceed in another branch, and it's just about unrelated groups. So before I said that free groups have decidable word problem, so now the natural next question would be to talk about groups where we have one relation, not zero. And the presentation is like this. You have finitely many generators, only one relations R, and R is just a word in these generators. And actually the class of unrelated groups is quite rich, and these groups appear also a lot in topology and have rich geometric properties as well. One, as a first example, I would take Z square, which is this group. We have only one relation, and this is also the fundamental group of a torus. And then one could generalize this to fundamental group of G genus surface, orientable surface. And the relation now is like this, where this should be the identity. Another example is the fundamental group of the Klein bottle. Again, we have only one relation. A generalization of this would be also the fundamental group of non-orientable surfaces. And there is another class of examples called Baumschlag solitary groups, which have very bad behaviors in a lot of senses. Like many times when one searches for contradictions or counterexamples in group theory, usually this is the class where you look for. And one of the main classical results about unrelated groups was proved by Magnus in the 30s, where he provided an algorithm to solve the word problem for the whole class, which is surprising as they don't, like in the geometric level, they don't share many properties in common, like they differ a lot. And another one of his results is about three subgroups of unrelated groups. And it says that whenever you take a proper subset of A such that you omit one element appearing in R, then that subgroup generated by that proper subset would actually be free. For example, if we start with this group, then if we choose A and B as a subset of generators, since C appears in the relation, but we are omitting C, then this group is free of rank 2. And then in the late 60s, there was a result about a bit of classification of these groups. And this result that says that if the relator is a proper power of a word, then the group is actually hyperbolic. So this result saying that unrelated groups with torsions are actually hyperbolic, and whenever the unrelated group has torsion, it's a better option, since we know a lot of stuff about hyperbolic groups, as they are what it's called automatic groups, and it's easy to study them using automata theory. And then there is another result saying that if the word is not a proper power, then the group is what is called locally indicable. And this says stuff about finitely generated subgroups. And it says that any finitely generated subgroup inside the group, you have this homomorphism onto, which can can be made surjective. And this is also good because it gives some left orderability properties for the group and its subgroups. But even though we know some stuff about one-related groups, we still don't know much about them. Like the conjugacy problem, which asks if two given elements are conjugate of each other, it's still open. And it's very surprising, as it's one of those rare classes where the word problem has been solved for a long time, but the conjugacy problem remains still open. And then there is the isomorphism problem, which you give to two groups, G1 and G2, and you ask if they are isomorphic. But this problem is undecidable, as you cannot construct an algorithm which tells you yes or no. And there is the problem of coherence, asking if a finitely generated subgroup is actually finitely presented. And this one is asking if if a subgroup contains Z square, it's not hyperbolic because Z square is not a hyperbolic group. But if this question asks if it doesn't contain Z square, is it hyperbolic or not? And this one is still also open. Okay, and now I will talk about some other decision problems and how they relate to the word problem. And the first one is the submonoid membership problem, where we have a monoid, we choose a submonoid inside of it and ask about membership of elements of the monoid inside of A. And we want to get an algorithm which takes as input a word written on letters of A and decides if that word belongs to the submonoid N or not. And actually, there is something called decidable submonoid membership problem for M without relation to any of its submonoids. And this is a bit stronger as we are asking for an algorithm which is independent of the monoid you take. So this takes as input both a submonoid and a word, and it provides the answer yes if the word belongs to the submonoid. And yeah, as I said, the free groups, free monoids have this property. So you could take as examples those free classes or ways. And the same is about the subgroup membership problem, where we start with a group, we take a subgroup, and whenever we have a word written on the alphabet, but now since we are in a group, the words can be written also using the inverses of the element on the alphabet. And we can ask the questions, if is this word element of a subgroup? And we would like to get an algorithm to decide that for us. Yeah, this is one of the results that this also holds in free groups. So the next step would be to talk about groups with one relation. And this is actually quite a recent result. And this is my line manager in Norwich. And he showed that you can actually have groups only with one relation, and you can get a submonoid inside, which is finitely generated, and there is no algorithm to decide the membership problem on that submonoid. And I will talk a bit about how this is proved in the next slide. But there are two other problems, one problem and one question in the project we are working on. And it asks to kind of give a boundary between those monoids which have decidable submonoid membership problem and those that don't. And the same problem also for one relation groups. And in particular, there was this question in the project that if you have a monoid which is of this form, where the relation is only one, but the relation is not of the form u equal to v, but just w equal to 1. And we wanted to know if these have decidable submonoid membership problem. And I will talk about the answer to the questions in a bit. But for now, I will talk about some counterexamples related to membership problems. And those main counterexamples are kind of the best ones we know. And they are found in the family of right-angled torting groups, which are groups finitely generated where the relations are only commutations. So, and the way to give the group is actually encoded in simplicial graphs that Gramos talked about last time. So we start with finite graphs and we label the vertices. And whenever we have an edge between those vertices, we are going to get a commutation between the generators corresponding to those vertices. For example, the group G1 corresponds to the graph gamma 1, and as generators are the vertices of the graph A, B, C, D. And as the relations, we get just the commutations between vertices that share an edge. So A and B share an edge, so A and B commute, B and C share an edge, B and C commute, C and D share an edge, C and D commute, and the other pairs are free of relations. And this is denoted as AP4, which is arting group of the path P4, which is this path with length 3 and 4 vertices. And similarly, there is this square group, G2 corresponding to the square. We get the presentation similarly. And actually, this is just a direct product of two free groups. The first free group would be A and C, and the other free group would be B and D, and it gives this group. And one of the results was that the square group actually has undecidable subgroup membership problem. So you can find the subgroup H inside of this group for which you cannot decide membership problem with using algorithms. And similarly for the first group, it was shown that it has a submonoid inside for which you cannot decide membership problem. And yeah, and usually the work that we have done so far, it's basically sometimes just having injections of these groups inside our new groups, and this would just immediately give the answer. But also another new result that we have now is that we actually don't need the full injection. We just need kind of the minimal stuff coming from the proof. And I guess it's a new way to prove undecidable membership problems in monoids. And this is an answer to the question that I asked before for groups of this form or monoids of this form. And it says that there is actually a group in this form. And interestingly enough, this group, I mean, the word that defines it is actually positive words on A and B. So we can also consider the monoid with the same presentation. And actually this monoid is a group and it's equal to the group with the same presentation, because from the way we define W, we get that both A and B are have left and right inverses. So once you have a left and right inverse in a monoid, you actually get an inverse. So this happens for both A and B. So this was the first kind of examples where we found undecidable for this kind of group. And here actually we use the embedding of AP4 in our group, and the results is kind of a corollary from the slide before. However, I just want to point out this remark that there are groups with one relation, and you cannot find a presentation of this form with VW positive. So there is a nice paper in France for Z-square actually that tells us that we don't get a presentation for Z-square with finitely many generators and only one relation where the whole relation is positive.
Islam, can I ask you what is a positive relation again?
So this W doesn't use A minus 1 when it's written. So it's just A, B, and positive powers of A and B. So it doesn't use,
okay,
like if we write the Z-square relation, it would be AB, A minus 1, B minus 1 equal to 1. But there we use negative powers for A and B. Okay, and as an immediate corollary is that we actually have monoids of this form, which are called special monoids with undecidable submonoid membership problems, because this is the example as it's both a monoid and a group. Okay, and finally, I will talk about unrelated monoids, and in the first slide, I will try to explain what the presentation means for the monoids. So we have finitely many generator for the monoid, one A1 to AN, and we have a relation U equal to V. And both U and V are words in these generators. And yeah, they should use only non-negative powers, as in the monoid, we don't have inverses. Okay, and here is a depiction of what, like if we have a word which it has U as a subword, we can actually substitute that subword U by V, since we are allowed to do that by this relation. But also, if we have a word which has V as a subword, we can also substitute that by U. So these are kind of the elementary moves in words in a monoid we can do. Wherever we see U, we can write it as V, or whenever we see V, we can write it as U. And this is just a reformulation of the word problem in monoids. And it says that if you have two words, A and B, like W0 and Wn, can you find a finite sequence of these elementary moves by substituting U with V or V with U to conclude that they are equal or not? This is just a reformulation of the word problem for monoids. And I guess one of the easiest examples would be if both words U and V have equal length, then the monoid has solvable word problem. And if someone wants to take this as exercise, it's basically doing combinatorics and a bit of counting on the monoid, which would be a nice exercise. And the next easy case would be this, where you have one of the words actually has bigger lengths, but it doesn't have self-overlaps. And a word is said to have self-overlaps if it can have a subword which it starts with, but also it ends with. Like the word AB, BAB starts and ends with AB, so it has this self-overlap. So this is the word, and we can write it again here, but there is something that it has in common. Like in this case, S denotes just the AB, the thing in common, and then L is the thing that remains after we put AB here. So L is just ABB, and R is BAB, the thing that remains after we write AB here. And in this case, this is a word that has self-overlaps. And this theorem is about when the bigger word doesn't have self-overlaps. And this result says that monoid would have solvable word problem. And actually, the algorithm that just substitutes the bigger word by the smaller word gives a complete rewriting system for the monoid. And this complete rewriting system is something Oran has talked about in his talk. And it's basically, whenever you see the word U, you substitute it with V. And this gives the desired properties, as this is Noetherian, as every time you substitute U by V, you reduce the length of the word. And at some point, you arrive at a place where you cannot do it anymore. So it terminates. And also, there is a way to show when the word doesn't have self-overlaps, that whenever you apply this move in two different places, you can actually arrive at a common word, like you get the confluent property. Because if it doesn't have self-overlaps, whenever you meet the word U, whenever you have a word, it's going to be U, another piece, U, another piece. So you can substitute them in a way that they don't intersect. And there is this classical case where one of the words is just the identity, like V is 1. And this is called a special case. And here the word U is also allowed to have self-overlaps, but it still has a decidable word problem. And actually the solution for this goes through the solution of the word problem for one-related groups. As one looks at the element of the monoid that are units, which have left and right inverses, and that actually, the set of units gives a group, and that group is a group with one relation. And you can use the fact that groups with one relation have solvable word problem to encode that information for the monoid as well. And this result actually holds in a more general setting, as it holds even if you have more than one relation. But I'm concerned only for the one relation case, so I put this just as a remark. And now I'll give two results which kind of reduce the word problem for one related monoids to some not bad looking cases. So the first reduction is that whenever you have a one related monoid, the word problem for that is equivalent to the word problem for a monoid with only two generators. So you can reduce the number of generators and you still have only one relation. And another better reduction is this, that says that if we solve the word problem for these two monoids that look like this, then we can solve it for the whole family. So whenever you see a monoid with many generators and one relations, you can perform some procedures to either arrive at one of these cases or to know that the word problem is solvable. And if you arrive at one of these cases, it might be the case that you still know that the word problem is solvable, or that it's still it's still open or something like that. And now I'll just provide this interesting relation of word problem for one-related monoids and groups, because it's important to bring theory and monoid theory to group theory, as it's considered easier to deal with, as groups have more structure than monoids. And this result says that if you have a monoid which has undecidable word problem, which has n generators and r relators, then you can actually encode that information in another group which has some generators, finitely many, and has this many relations to n plus r plus 5. And this group is gonna still have undecidable word problem. And recall that for the word problem in one related groups, we are concerned only with two generators. And yes, we have only one relation. So we would have n equal to 2 and r equal to 1. So this number would be 10 for us. And a corollary of this result would be that if we solve the word problems with groups with 10 relations, then the problem would be already decidable in monoids with one related. But it seems like we are bringing a very innocent-looking problem in monoid theory to one in group theory, which can be very problematic. However, there is no counterpoints here, as the smallest number of relations for groups which have undecidable word problem was 12, as I said before. So for 10 is still open. So one could find a way to use this theory for monoids maybe. And here I just provide a small digression to the third structure, which was between monoids and groups, and it's called inverse monoids. And here actually they provide a theorem to kind of attack the word problem for monoids, which was basically just to consider these two examples. And they embed it into inverse monoids. And inverse monoids have richer structure, so it makes sense to bring problems from monoids to inverse monoids and study them there. And actually, they conjectured that the word problem for inverse monoid in one relation is solvable. But again, it was my line manager who found the counterexample of an inverse monoid with one relation, but undecidable word problem. But still, the example that he provides, it's not of this form. So there might still be room to go through the word problem for the monoids using word problem for certain inverse monoids, not like you have to work with cyclically reduced words, something like, for example, this is not, like it starts with I minus 1, ends with a. And also reduced word, which this example, the word W is not reduced. It can have a minus 1 inside of it. And in inverse monoids, we cannot necessarily substitute a minus 1 with 1, because that's not the definition of the inverse. So there is still a way to go through this route to solve the word problem in one or later monoids using inverse monoids. Okay, and finally, I'll talk a bit about this, one of the remaining cases, one of the two remaining cases about monoids, which is this one. And there is a theorem by Adyan, which was actually the main guy from Russia that worked a lot on one or later monoids. So for his case, he proved that this monoid is actually left cancellative. So whenever you have this equality WU equals WV, you can actually cancel stuff on the left, but not necessarily on the right, because if you could cancel in the right, you would also cancel this A's and you would get just BQ equal to 1, which would be something we already have an answer for. And there is also this algorithm, which uses left cancelability to work equality of words in the monoid. So if we start with two words, bx and by, which both start with b, then we can just cancel the first letter b and work with two shorter words. Similarly, if they start both with a, we can cancel the starting a's and work with shorter words. And if one of them starts with b and one with a, we can flip sides, it doesn't matter. So we don't have to consider the other case as well. So we can just substitute the letter a with this relation that we have above. So we substitute a with bqa, and now we get two words which both starts with b. So we cancel b, and we get this pair of words to consider now. But here, notice that the length for the first word is a bit shorter, but the length for the second word, it's actually gotten a bit bigger. And I think there is a problem that can remind us of what's happening. And if we consider still this case, but we pass to binary representation. So we choose to represent A by number 1 and B by number 0. Then, yeah, here I did the presentation only with one example, this one. So we would get this type of things. So now the words are just strings of zeros and ones. And the first step before was to cancel the first letter. So here the binary representation is a bit, it works from left to right, like this is the first letter of the words. It could have been done the other way around, but I was too lazy to do it. So here we can just cancel the last digit of the strings. And what this means in the decimal system is that the first number is divided in half after removing the last 0. The second number is divided in half as well. Now, if the binary numbers and both in 1, we can still cancel both ones. And here, actually, we subtracted 1 and divided by 2. So this would be the decimal representation of what's happening here. And the third algorithm, the third step of the algorithm is this one, where we had to go through the root of the relation. And here, the first number is divided by 2 again, because the 0 is removed. But the second number, this depends on what the relation is. So here it was this relation which gives this number, and actually this one happens here, but there is room to have a lot of expressions here. On the other hand, the other remains always the same. Okay, and this is something that looks like something we have seen before, but in tuples. This is just a computation to make sense of this last time. And this is actually something that looks like a Collatz function, like the one we started with. So these are functions of the form from n to n, and which are given for a given natural number p, and we consider the residue classes for other numbers. So we send, okay, so we have these numbers a0 to ap minus 1 and b0 to bp minus 1, which can be irrational. But the point is that the outputs should be natural numbers. Like in the Collat's conjecture, you can have this 1/2 numbers or 3/2, but the outputs is always an integer. And there is a result of John Conway on the 70s that says that if you cannot find an algorithm that takes as input Collat's functions and a natural number and decides if this sequence actually reaches 1, which is like in some sense saying that some Collat's functions are actually undecidable. You cannot write algorithms to prove if they reach 1. And there is this slight modification, which is something that actually looks more applicable to also a single Collat's function. And this says that there is no algorithm that takes as input a function, a Collat's function f, and decides if this sequence reaches 1 for all n. And this is something that brings some doubts to the word problem for the monoid as well, because the word problem for this monoid is quite related to the Collat's function it represents in this binary representation. And finally, I'll just talk about the prefix and suffix membership problems, and I will just give a general frame of how these problems relate with each other. Okay, so we start with the monoid of the form u equals v, and we can look at the prefixes of u and prefixes of v and consider the submonoid that those prefixes generate, and the same for if we consider the suffix monoid. For example, if we start with a monoid with these ABC as generators and the relation is AB equals ACA, then the prefixes of AB are A and AB, and prefixes of AC are A, but we already had A, so we don't put it again. And then it's AC, which is here. And then there is the whole prefix ACA. But by definition, ACA is equal to AB, and we had AB before, so we don't include it again. And then there is the suffix monoid as well. And one thing to take into account about prefix and suffix submonoids is that they depend quite a lot on the presentation of the monoid or the group that it's given. Like here, there are two presentations of the integers by two different relations. And the prefix monoids actually don't agree. Like the prefix monoid for the first presentation is the whole group, but the prefix monoid for the second presentation is just one side of the line, like the negative side. And there is a result of Guba, also a Russian mathematician who worked in one or later, who still works in one or later monoids. And he related word problem with suffix membership problem for the monoid. And it says that for a given monoid like this, you can find the one or later group given like this, where the word problem gets reduced to the suffix membership problem. And as a remark, we have a monoid which has decidable submonoid membership problem. Then in particular, it has suffix membership problem because the suffix and prefix membership problems are just particular cases of submonoid. So this is a corollary like fictitious one, like it would work if things worked, but so it says that this monoid would have decidable word problem if positive one-related groups have decidable submonoid membership problems. But we have shown that that's not the case. But in any case, it motivates the study of the submonoid membership problems and kind of to draw the boundary where the membership is decidable or not. And lastly, this in the right-hand side of this diagram, you can see the main problem is this one word problem for one-related monoids. And this is equivalent actually to only considering these two cases. You see that from big A, we went only to two generators, and the relations now have only these two specific ways. And this would also, if we solve the word problem for these types of inverse monoids, we would get a solution for our monoids. And this is the relation how this, for example, the prefix membership problem for this gives the word problem for this monoid. Same the prefix membership problem for a group of these forms. And this is a bit in red because here we actually also found the counterexamples where the prefix membership problem for these types of groups is not always decidable. And yeah, it's just a way how prefix and the word problem relate for these solved structures. And thank you for your attention. I hope you liked it.
Thank you. Thank you very much. I think this is the time for questions. If you have any questions. I don't. So if you have any questions, just turn on your mics. Nëse keni pyetje, nëse bën Islam tash me heq këtë full screen që e ki.
Po.
All right. Okay. Tash më legu. A ka dikush në një pyetje? Is there any question? I have a somewhat general question. You mentioned earlier a couple of times motivations from algebraic topology, and what is the geometric theme of these problems that you are considering? What is the geometry behind, if there is any? Because yes.
For one related groups, actually, there is, till now, there has not been something that holds in common for all of them. And that's why it was very surprising. It's very surprising that the word problem has been solved for all this class of groups. And actually, the solution is algebraic, so it's not geometric in nature. But now, recently, there is this mathematician, Danny Weiss, who works with one related groups, and I think they found something that works for the whole class, which is called immersions, something immersions. But for the monoids and inverse monoids, the geometric structure is less rich than for groups. Like for groups, you have the fundamental group, and you have also the Cayley graph to use geometric tools. But for monoids, these are not always kind of good behaved. So yeah, I think the geometric nature for these problems depends a lot how the word that defines is given combinatorially. Like for example, in the case when it's a proper power of a subword, then it's gonna be hyperbolic group, which has a very good geometric nature. But if it's not a proper power, then it can behave very badly, as bounds like solitary groups do.
Hamdi, do you have a question, or does anyone have a question? Nuk po të dëgjojmë.
Mundesh me shkruaj në chat nëse do të pyet.
Okay, I was just wondering if the algorithms for the decidable word problems are implemented in an algebra system.
Okay, so there are a lot of interesting classes where you can have implementations. Like usually the program that mathematicians in group theory use is called GAP, and there you have a lot of implemented algorithms for this stuff. But I don't know if the one related group is implemented for all the relations. I guess it can be, because it works only on by induction on the length. So it should be there.
Thank you for your question, Hamdi. So are there any other questions? I don't see anyone. In that case, I would like to thank you again on behalf of everyone for this wonderful talk. And
Thank you for having me.
We hope to see you soon. Faleminderit shumë, Islam.
Faleminderit shumë për ftesë.
Shihemi shpesh. Hamdiu veç po dua të kit, kështu që. Faleminderit. Edhe faleminderit gjithëve të pranishëve online. Edhe faleminderit edhe një herë.
Faleminderit gjithëve për prezencën.
Mirupafshim.
Mirupafshim.